I started eating out of bread. I also had dessert after. That's why I think a big deal. Share. How hungry this guy is. That's pretty good. Yeah. I don't like eating
Okay. Just because it's chocolate, he doesn't mean it's a monster piece of bread.
I'm just hungry.
She's a very normal size. Something about that.
Oh, shoot!
Like a snack or like a chocolate muffin? No.
I got really excited for this.
They all got in your class. Those were delicious. Those were so good. I'm so glad you're such a friend.
Further in the court. Okay. Okay, maybe just once more. Okay, so at the end of today, we're going to look at the final exam preview. So by the end of today, you're going to have questions to review and things like that. So we'll start to arm up for the final exam. And we only have one class after today. So what did we talk about last time? Well, let me just preface again. We're going to talk about factorial ANOVA, and then we're going to hopefully get into regression, and then by the end of next class, we'll have covered regression and a little bit of multiple regression. So that's where we're headed. Big picture, what did we talk about last time? Factorial analysis of variance. Okay. So what's factorial analysis of variance? Well, why we use it? Primarily because we're looking for what? Interactions, right? Interaction. So what's an interaction? Right? What's an interaction between variables? So we have a dependent variable, and then we have an independent variable. In regression, we're going to call these sometimes response variables and predictor variables. And let's say that's x1 and x2. So let's say x1 has 2 levels and x2 has, say, 3. What would be a main effect for x1? Well, a main effect for x1 would be a mean difference on levels of x1, right? On levels of x1, so that'd be the main effect for x1. Main effect for x2 would be mean differences on those levels of x2. And what would be the interaction effect here? So if I go x1 by x2, maybe like a little star for like multiplication. x1 by x2, how do we interpret that interaction? What would it mean to us? If there was one. What's one way of saying? So we've got, say, dosage of drug as x2, and we have, say, age as x1. So maybe dosage here is 1, 2, 3 milligrams or whatever, whatever groups you want. And here we have young and we have old. Okay. So if we said there was an interaction between those two factors, what would be our interpretation there?
It could be that the effective dose is not the same at each level of age.
There we go. That makes sense? The effective dose is not the same at levels of age. In other words, the effective dose depends on or is contingent upon what age you're looking at. Right? What age you're looking at. So think of it practically. Think of it practically and saying, you know, there's a dosage effect of melatonin. There's a dosage effect. If that dosage effect, maybe as you increase your melatonin, you sleep more, that dosage effect, if it's consistent across young and old, if it's the same thing across young and old, then there's no interaction. But for there to be an interaction, it suggests that the dose effect changes depending on what age you look at there in terms of young versus old. How that curve changes, well, we'd have to plot out the data like we have here, but it suggests that there's some kind of contingency, some kind of dependence on the other factor, So how does that translate into a graph? Well, that translates into a graph by, what did we say? If there's no interaction, then let me just do a simple thing like this. If there's no interaction, then what is true? They're parallel, right? The lines are parallel, okay? So let's ask this question, which is a really important one. In any sample data that you can have, do you think there's going to be an interaction in the sample data? So for any sample data that you have, do you think that when you plot things out or observe the means, do you think there's going to be an interaction in that graph, in the sample data? So in that sample data, do you think there's going to be an interaction? Think. What is it going to be 99.99% of the time when you look at an interaction graph? Do you think those lines are going to be parallel? No, right? They're not going to be parallel. Okay, 99.99% of the time, unless it's very weird or special data, that these lines are not going to be parallel. So in other words, in any interaction graph that you look at, you are going to see evidence of an interaction in the sample. You're going to see evidence for an interaction in the sample. Okay. Now, why is that? Why are you going to see that? Well, that's just because of you're measuring things on a continuous scale, because y is continuous here. So basically, these cell means, they're not going to follow the exact same trajectory. There's going to be some difference in the sample. Does that make sense? Now, do we care about that difference? No. What do we care about? So if I look at this and I go, hey, those aren't perfectly parallel, and I stand by it and I go, I have an interaction in the sample, right? I'm standing by it now, right? I have an interaction in the sample. What's a fair thing for someone in the audience to say?
It's just error or chance.
They say, we don't care, right? They say, we don't care about the interaction in the sample. Why did we collect the sample data? Merci beaucoup. Thank you. Why did we collect the sample data?
So it could reflect the population.
So we can say something about the population, right? So the only reason, again, why we're collecting the sample data is to get some kind of idea of what might be going on in the population. That make sense? So it's important to realize that you're always going to have an interaction with sample data practically, but what you're really interested in is whether this suggests non-parallelness of population cell means in the population. So here'd be the wrong way of doing things, and I've seen this, and it's kind of, the reason why I'm highlighting this is because I've seen sometimes people do this, and they go like that, and they will literally stand next to the graph, right? They will go like this, and they'll say, I didn't find any interaction, right? I didn't find any interaction. Well, you do have an interaction in the sample, but when they say, can I stand next to the graph and say, I didn't find any interaction? If I said that to you, I'm presenting my research at the conference, and I said, I didn't find any interaction, what am I probably talking about? Population. So let's even think about this a little bit more. If I say, I didn't find any interaction in my data, what's probably going on? Now I say, here's my data, collected based on a certain number of observations, and I didn't find any interaction. Power, right? Power. In other words, yeah, you have an interaction in the sample, you just don't have the power to detect it in the population. Yeah, it makes sense, right? You see how it start coming together, right? I guarantee you this is an interaction in the sample. I guarantee you. Why? Because there's a different story being told for depending on which level you look at. There's a different story being told, okay? But in the population, we don't have evidence of an interaction, and that's most likely, in this case, I mean, it's probably gotta be, right? Due to just having insufficient power. Because there's clearly something going on in the sample. Now, who knows? You collect more sample data, what could happen? Well, maybe things straighten out, right? Maybe it straightens out. Maybe it actually doesn't do this as n increases, but eventually the lines do become parallel, and we have to account for that possibility too. But if this effect, right, if this effect remains as you collect more sample size, you are gonna get your desired p is less than 0.5 or whatever alpha level you're using. Does that make sense? So let's be aware of that yeah, there's an interaction in the sample, But we don't really care about the sample, we care about the population. But don't stand next to a graph and say there's no interaction in the graph, because there is, it's just that you don't have evidence for one in the sample. If you actually try, if you wanna justify that to yourself, try to draw two lines that are, like I can't do it, right? Try, go like this, go, are those lines parallel? Nope, try again. And that's what sample data is basically doing, is that there's gonna be, even if they're perfectly parallel in the population, they're not gonna be parallel in sample data. So the search is for interactions. The question that we're gonna have to ask when we look at the interaction graphs, so we've talked about those graphs, right? We talked about the graphs. The question we're gonna have to ask is, you know, the complexities of modeling now are increasing because we don't have only one main effect. We don't have two main effects. We have the interaction effect. So here's the question, right? Here's the question we need to ask, and we're gonna be asking into the spring. And can you still say there's a main effect for X1, even if there's an interaction? So is it fair for me to say, can I still say, well, the young are different from the old on sleep, even if there's an interaction here? This is sleep hours slept or something. So does everyone appreciate the, can I say, well, if this comes out and I go, well, young sleep less than old, even if I found an interaction effect. So let's say I found all effects. I interpret that main effect. What would that be like in our table? The analogy in our table would be to find a textbook effect and go, textbook 1 is different from textbook 2, right? Textbook 1 is different from textbook 2, even if there's an interaction effect. Can I do that? Something to think about. Who says yes? Does everyone get the question, what we're asking? So we have an interaction effect, right? There's an interaction effect that we found, and it comes out to be statistically significant and everything. I go, well, there's an interaction of X1 by X2. Could I still just interpret this, because I got an effect for this too, could I still say there's a mean difference between young versus old, even if I found this, which would, the equivalency here would be textbook 1 different from textbook 2. So if I found a difference between textbook 1 and textbook 2, even though I found an interaction, can I still interpret that mean difference and say, well, people who use textbook 2 achieve more than textbook 1? Everyone on board with the question? Okay, let's make sure. Anyone not on board with the question? Okay, so now which one, who would say, yeah, go ahead? Who would say, go ahead, interpret that mean effect? Who would say, don't you dare? Right? Who would say, don't you dare? Okay, who says interpret away? Nothing wrong with it. Okay, who says, okay. So let me start with the ones who say don't interpret it. That's not the thing to do. Give it a shot. Why not? Well, why would you say don't interpret it? Why would you say interpreting this main effect should not be done if this is occurring?
Because just because you're not taking into account that interaction in the main effect, that interaction still, the main effect is still dependent on the interaction.
Okay, so this here is still like a statistical truth, right? There's still a difference between young and old, but the issue is that if this is occurring, which one tells you the biggest story of your data? Is it this? No, it's this, right? Does that make sense? This one here, if there's no truth in data, but let's say for a second, the closest thing to the truth in the data would be this. Make sense? This is the most complete story, right? The most complete story. We talked about examples last time. Give me an example. So you have a 7-year-old person taking a medication like melatonin, thinking this will help me sleep, and it doesn't work. maybe it's not the best example, but let's say it says, oh, it doesn't work. But it says on the package, melatonin has been shown to increase sleep, right? What did I just say? When I said melatonin has been shown to have an effect on increasing sleep, what am I citing? Main effect, the X2. Yeah, the X2. And the thing is, if X2 comes out to be statistically significant, a good, eta squared and all that, that's still a true statement. It's still a true statement. The ANOVA gave it. It's still a true statement. So I can technically report X2, right? I can technically report X2, though I won't sleep well at night, right? Regardless of how much melatonin I take. I can still report X2 and it actually be a statistical truth of sorts, because why? Well, even if you have that interaction, I don't have to test the interaction. I could just test the two main effects. I could just say, you know what, I'm gonna get rid of this and just leave this in. Or I could leave them all in, regardless, if X2 comes out to be statistically significant, from one school of thought, I could still report it. Be more theoretically correct if I get rid of if I take out the interaction fully, and I just leave X1 and X2. Then X2 comes out statistically significant, I just say, hey, no, there's a dose effect. So what's the issue here? What's the issue? And it's not a small issue, and like I hinted at last week, this is only the beginning. Like, this is only the beginning of the issues with modeling. By the time May comes, you'll be, oh my goodness, why did statistics ever come into science? So, this comes out, I try interpreting this, let's just say we're being unethical, right? We're being unethical because this occurred, so therefore what term should be included? This term should be included, and this should take priority in the interpretation. But the thing is like I say, if you take out the interaction term, your X2 is still gonna come out to be statistically significant just because you didn't test the interaction. So there's two things here. There's one, the ethics of reporting the statistical model and interpreting it. And the other thing is what the statistics are telling you and what you're theoretically allowed to report. Does it make sense? So when the drug company says that melatonin works, or increases in melatonin have been shown to have an increase on hours slept, there's no guarantee that they're including this, because this would be probably what for their bottom line. Probably be a bad thing for their bottom line, because then they say actually it only works for young people. Past the age of 60, it doesn't work. So then they check with their statisticians, they go, what does the data say? Well, we have an interaction. I don't know, do we want that interaction? No. Then they can actually take it out and report this in the journal. So you have to be a very smart consumer of statistical research, and you have to look at that, and if there's no interaction reported, what's a fair question to ask? Yeah, why wasn't the interaction reported, right? Why wasn't the interaction reported? And if they say, we tested it, didn't like it, right? We tested it out, didn't kind of suit our practical, financial, political goals, therefore we left it out. Well, how serious am I supposed to take your research if there is an interaction? Now, if they say we tested it because we were interested, we didn't find one, so then we removed it after you've grilled them on sample size. Well, what was your sample size, effect size, all that? If there's legitimately no interaction, then in theory, they could always, take it out and just look at the two main effects. So that's actually fair to do. But if there is an interaction, but it doesn't accord with what you wanted to see, and it does make a difference in the outcome, then you definitely should be reporting that.
So anytime you run an ANOVA test, should you be looking at
It's a good question.
interactions,
Yeah.
period?
Good question. What do we think? So the question is, anytime you run an ANOVA test, should you be testing for interactions? It's not an easy question to answer it, but it's a relevant one. And it's like, do you have to include the interaction term when you test an ANOVA? Who says yes? Who says no? Who says Yes, only if it suits your financial goals. Only if it sells the drug better, right? Only if it sells melatonin. Well, here's the thing, what are we gonna, we're gonna have to make some decision on that. What are we gonna rely on? I mean, what's the guiding principle? There's a reason why your committees, when you submit your proposals and things like that, they're gonna say what? They're gonna say, did you just draw that out of a hat? And you're gonna say, no. What are you gonna say? It's based on what?
Data's
Based on, yeah, my theoretical predictions. I've done some research in the area, and I'm not just dropping this because I have nothing else to do. I'm dropping this because I have a good theory. You know, Newton kind of read a little bit of Newton, and Newton said, you know, you drop this, it's gonna do this, right? So that's based on prior research, on theoretical prediction, on an informed prediction on what's gonna happen. So if we were to assign some guiding principle to this, that would have to be it. That if you theorize an interaction, and you want to test an interaction, you theorize that, and you believe, you know what, I think there's an interaction in this data, and I think it's ethically responsible for me to predict one, then you should definitely include the interaction term. If, on the other hand, you've looked at your past 100 years of research, always go back in deep as history as you can, you'll find things repeat themselves. So if you go back in research and you say, wait a minute, nobody's found an interaction before, I don't have any inclination to look for one, I'm not interested in one, I just want to look at the two main effects, then at least idealistically, you could leave that interaction out and get away with testing those two main effects. Make sense? So what we'll say is, we'll say the theory guides the analysis. The theory is the guiding principle behind what analysis you do and why you do it. Now that's going away a little bit in modern times a little bit, because we have this, you know, big data, this machine learning and stuff like that, where if you're not doing scientific research, sometimes you just care about the statistical result. For instance, we were talking about this in my multivariate class yesterday, because we're talking about multivariate stats, and it's kind of like if you're trying to predict who will get cancer and who won't, maybe there's a gene that predicts the future of whether the disease will arise, maybe you're just interested in classification, right? Do these predictors classify those who get cancer versus those who don't? That's just raw prediction, and you just care if the algorithm can do the job. In that sense, this idea of going, well, does it accord with your theoretical prediction, doesn't really apply as much, because you're kind of like doing it as a brute force prediction task. You're not actually trying to account or explain the phenomenon as much. And actually, when you take multivariate, you learn about neural networks, you'll learn that sometimes we don't even care what those things are, we just want the prediction to work. So if I told you I have an algorithm that can successfully predict whether a person will get a disease or not, and it predicts at 98%, just give me a few data points, a few background information, and I will make the prediction. You may not care why, you just care that it actually works. So there is that vantage point. But if you're doing experimental science, and you are looking at things from a theoretical point of view, and you want to be able to explain the phenomenon, then definitely those things come into play, and you should consider whether to test the interaction or not. And theory should guide your research to some extent. Okay? So that's the idealistic, formal, kind of the way it should be done. But if you think about how is it done in practice, especially when you get outside the kind of like that ivory tower of academia and you get into the real world, where maybe that pharmaceutical company needs to make money, are you going to say to your client, now is it your theory to test this interaction, or isn't it? Probably not. You're probably going to test the interaction, see if it comes out, but hopefully not portray a dishonest picture of the data and take that into account. But you can see that's where it's conflicts of interest can easily arise there. And I've seen them arise, and I've quit consulting jobs because I said, no, I'm not doing this. I'm just not doing it, just because it's so dissatisfying. So you gotta really be careful. But you as the consumer of it, you gotta be able to say, hey, why didn't you test that interaction term? I wanna know more about the interaction term.
does that same issue come up when trying to publish data?
Yeah, it does. I mean, academia is an ivory tower, but, you know, people need to publish and they need to have career advancement and feed their families and things like that. So you just gotta, you gotta watch out for that and say, well, you know, be critical about that. Isn't it similar to like post hocs and contrasts? You know, like if I do like 3 contrasts, well, did you predict those in advance, or did you just run everything and then find out where differences are and then do contrasts? You know, so that kind of thing too. Are you able to predict differences? Do you have a theoretical rationale for it, or don't you? And those things do end up being in the model. So again, if I do this and I publish this, I publish that when I dropped the marker, it fell. Well, that's an empirical result. Whether I predicted it would fall is an entirely different story. So if I drop it and it falls, and then I write, I predict, and then I match the theory to what the data is doing, right? I match the theory to what the data is doing. Does everyone see it? If I do this and it goes, it dropped, I wonder why it dropped. I don't know. Things dropping. Newton. Hey, who's Newton? Okay, and I read up on Newton, I go, oh, that's why it dropped, and then I write my paper, according to Newton's theory, this will drop, and therefore I ran the experiment. Then that would be like false science. Okay. It'd be better if I read up on Newton first, devised the experiment, and then dropped it and say, see, this matched with my prediction. Okay. Makes sense? Same thing if we launch a satellite and it seems to orbit the Earth, that's a lot more powerful if we're able to predict that than if we just launch up there and see what happens. So those ideas come into here as well. That it should be based on theory. So at your dissertation proposals, thesis proposals, you want to have a theory-guided research question that you're asking. I mean, I'm gonna just ask the one question here is why not just fish? Just fish, right? So I've got like just 2 predictors. What if I have a third? What if I have a fourth? And I just start testing everything in sight. Let's just start testing everything in sight. You know, just everything. What's one problem with that from a statistical point of view?
Paralysis by overanalysis?
Well, yeah. Well, what could happen from a statistical point of view is if we think about it in terms of rejections of the null hypothesis, what happens? You know, I do like 20 different analyses, and then the ones that come out statistically significant, I treat as gospel. What's the problem? Type 1, right? With every analysis, you have a type 1 error rate. So the problem from a statistical point of view is if you totally exploit the data, right? If you totally exploit the data, how many of those results would you expect to come back statistically significant, but probably not even there? So I'm gonna exploit the data, run a whole bunch of tests, and I've run, say, 100 different tests on my data with no theoretical prediction. So I just run 100 different tests, and then I ask the question, what percentage of those would I expect to come out to be statistically significant, even if there's nothing going on? What percentage? So here's the problem. So I do the 100 tests, and then so I say, you know what, I'm not into theory, whatever. I'm just run the tests, right? So I run all the tests, and then I go, out of these 100 tests I did, 5% I rejected the null. Right on. Take those 5, woo, like that. I take those 5%, bring them over here, publish them, and go, this is what I found. What's the problem? It could be, well, yeah, but anything could be due to chance. What's the problem with that particular example of how that could possibly do it? I use 5% for a reason, then, right? It's your type 1 error rate, right? It's your type 1 error rate. Now that's going to accumulate over the number of tests, but what that type 1 error rate, what's the type 1 error rate really communicating to us? That when you reject the null with the type 1 error rate of 0.05, what's that street version of it? You know, I go, hey, I found something, but my error rate is 5%. What was our street version of that? Therefore, it's like, well, found the cure, but type 1 error rate, 5%. That means what?
5% chance.
Yeah, 5% chance. This is just a fluke, right? This is just random noise. So if you think about it, when we run several tests, first of all, our type 1 error rate is going to rise. It's going to get larger. but you would expect some results to come out just due to chance. You would expect statistically significant results to happen even when there's nothing going on. Does that make sense? So that's what you have to guard against this. That's the problem from a statistical point of view of fishing. If you fish the data, you expect some stuff to just happen due to chance. That's often called in research called the file drawer problem. And the file drawer problem is that idea that sometimes the results that are published are actually, it's kind of a scary thing, but the results that are published could just be what? The type 1 errors, right? So what happened to the 95 studies that weren't published? We never know about them, we never learn about them. So that 95% of studies that I said didn't work out, they get filed away, file drawer, in here, and we publish the 5%. So therefore, what you're seeing in the literature when you get the latest edition of American Psychologist, and you look at it and go, oh, interesting, they found a cure for the disease, or they whatever, interesting. If you're not aware that there's 95 studies here that didn't find it, you could just be theoretically interpreting a type 1 error.
Wow.
Yeah, no, I mean, that point in this type of thing, I'm kind of like, that's my career, is to analyze that kind of stuff and go, what the heck is going on, right? And I've written a little bit on it, and many other people have written on it too, is the way that things are published is you got to be very careful, because what are you actually seeing in the journal? You know, if you look, here's the thing, is if you do an experiment, and it's an intelligent experiment, a good experiment, it's based on good research and things like that, and you submit it to the journal, because you think that this phenomenon should happen, and let's say it doesn't turn out, okay? Let's say it doesn't turn out. And the editor of the journal says what? Says, no, oh, come on, you didn't find anything? Get this out of here. What's the problem with that? Well, if they only accept the ones that do find things, then when you read the article and you go, you have no way of basing this among the population of papers that have tested the phenomenon. So if you're not aware of the 95, how are you supposed to know if there's a phenomenon going on based on just one paper? Right? That's a real problem, and it's something that, I mean, yet from a methods point of view, it's very concerning, and people have written on it saying journals should actually accept all publications, because a negative result, what's a negative result? You know, you don't reject the null or whatever. Variance explained isn't very high. The negative result is actually just important as the positive result, okay? I mean, what's the argument towards that historically? There's a historical element that at one time I think made sense. Now it doesn't quite as much. Why in the 60s, right? In the 60s, they go, oh, we can't have non-significant results. We got to get the significant results only.
Or experimental design, or.
Well, here's the thing, right? So if I submit the study and it doesn't reject the null, in the 60s, they're like, you know what? We only have so much journal space, and it's expensive, right? It's expensive to publish a journal, right? To print all that and stuff like that. So that's expensive. So we have to basically just publish the results that come out. We can't publish everything. That's fair, I guess. But today, especially with computer, with cheap storage space and things like that, you should be able to look up depression linked to anxiety. How many studies find it? How many studies don't? So you can discern whether there's the statistical effect, right? And we know that some studies will find it and some studies won't. It's not as simple as dropping this and every study finding it. That's why oftentimes in physics, if I do this and it doesn't fall one day, right? If I go, like it floats, then what am I doing? I'm on the phone to my colleague. I'm going, try this right now, do this right now. And then they try it, and within like 2 days, they're like, markers no longer drop. The gravitational forces are failing, right? That happens very fast. But what's the difference between that and a lot of social research? One experiment does this, the other experiment does this. Next one does this, the other one does this, the next one does this. So if you're gonna interpret what's published in the journal, you should have a comparative analysis of how many find it, how many don't. Okay. And that's sometimes done with meta-analysis. People are trying to do that with meta-analysis, looking at the whole body of research to try to find how many publications actually find the effect and how many don't. But it's difficult to do if we don't know how many didn't find it. So what's the way around that? A little bit of sociology of science there, but it's important, right? Is there a way around that? I mean, you're going into research and you do research and you're getting to say, how do you know whether this thing is an effect? Whether it's something that's occurring or if it's just maybe a type 1 error. I mean, what's the roundabout for that? There is a roundabout. What can you do? How do researchers get around it? Like, I know some researchers in the department where they don't have that, they don't have that issue, right? They don't have that issue because when, like, Luke Conway looks at a research paper and goes, oh, found something. He's so knowledgeable about the research area that he knows basically what's going on and what's not working because he's consulting with colleagues, he goes to conferences and things like that. So if you're familiar with the research base by other means, then you can evaluate whether that has kind of any merit, other than the research publication publishing all positive and negative results. Make sense? But something really important to figure out. So we see this issue, we see the publication issue, the replication issue is something, again, maybe you're talking about that in your research methods class, but replication should be done, especially with social data, because of those random errors and things like that. So if I found an effect for melatonin or whatever, this should be able to be replicated over and over and over before we can say there's actually something there. One study will never be enough. There's actually been some studies showing that a lot of research isn't replicable, that when you do it again, the effect doesn't turn out. So these are all things to be concerned about. So getting back to the theory of factorial ANOVA, there's our melatonin dose, there's our high, low. We ask the question again, does any given score in our data deviate from the mean of all data? We talked about the within cell. What's the within cell variability now, right? Do I have a data table? Within cell variability is that variability happening within the cell now. There's our new error variability, right? That's our error variability. So the question of why observations are different within the cell, what's the fundamental answer? Well, we don't know. It's due to error. And if you do know why those observations are different, then you should be doing a different experiment or adding another factor. So it's the within cell variability. Talked about the cell effect. We talked about that they sum to 0. And then we defined the interaction effect. Okay? The interaction effect is defined, and we get to eventually, after a little bit of work, we get to, where is it? It's somewhere. There it is. There's our ANOVA summary table for the two-way factorial design. So we have the effect for A, which in this case is rows, the effect for B, columns, and then we got the A by B. There's our interaction effect, and there's our error effect. So the interaction effect is made up of a term called AB cells, okay, AB cells, minus the effect for SSA minus SSB. So you can see what's happening here. We have the total variation. The total variation is being partitioned into A, B, interaction effect, and error, okay, and error. And then it proceeds just like we would in the one-way ANOVA. We divide by degrees of freedom. We divide by degrees of freedom, so we take SSA over degrees of freedom, and that gives us our mean squares. Okay. What's a mean square? What's a mean square? What is it?
Variance, what it, like the equation?
Yeah, what is it?
Variance over.
It's the variance, right? It's a variance. So this mean square is a variance. This mean square is a variance. And then we have the variance here due to the interaction. And then we have the error variance, right? And then we have the error variance. So remember, those mean squares, they're actually variances based on different quantities. So when we look at this, we get our F statistic for each effect. So F for A, F for B, F for A by B. Okay. And in each case, we are dividing by MS error. We're dividing by MS error. Now, why are we dividing by MS error here? Well, worked out in the notes are what's called the expected mean squares. the expected mean squares. What were the expected mean squares in the one-way analysis of variance? Well, the expected mean squares was what are these quantities actually estimating? So if I took expected values of these quantities right here, these three quantities, what are they actually estimating in the population? What are they estimating? Well, when we do that, and it's a mathematical exercise that's in the notes, when we take those expectations, those long-run averages, we see that if we divide by the error term, we're able to isolate the effect we're interested in for the given term. Okay? We're able to isolate the effect we want for the given term. So if we look here, for instance, for expected mean squares for factor A, well, the expected mean squares for factor A is equal to error variance alone under the null hypothesis of no treatment effect. Under the null hypothesis of no treatment effect, the expected mean squares is equal to error variance alone. So if it's equal to error variance alone, see there it is where our AJs, they're squared, but those are our AJs. If under the null hypothesis, this is 0, therefore the expectation is the error variance, then that means the way to get our F ratio is taking MSA over MS error. That's the logic of why we're doing that when we're taking that F statistic. Now, those are important, those are details for understanding why that F is being taken the way it is, and that's through the procedure of expected mean squares. Through the procedure of expected mean squares, we're not focusing a lot on that in terms of taking expectations because it ends up just being a mathematical exercise. But here's the big picture of this, is that when you look at the F statistic, and you say, hey, why are we defining this F statistic as MSA over MS error? Why are we doing that? Why are we going MSA over MS error? What's the reason? What's the reason? Now you have your foot in the door and you'll know what the reason is. What's the reason for that? Why are we going MSA over MS error to get our F ratio? Why not do this? MSA over MSB to get this. Now if I said to you, I want to compute the effect for A as MSA over MSB. What would be your grounds for disagreeing with that? Then someone else says, no, the correct error term is MS error. You got to do it by MS error. You can't divide MSA by MSB. What's the grounds for that person saying it has to be MS error? Because, yeah, you're close, because that's the way what turns out. Can't just say the math. Can't say what's the way the math turns out. That's the way when we took the expectation of MSA and set this to 0, saying there's no treatment effects, the expectation of MSA under that null hypothesis of no treatment effects comes out to be error variance. Therefore, this is the only thing in this term that's kind of, you use the word polluting the term, that we need to get rid of. Because look, if there's an effect for treatment for A, then this is going to be not 0, right? That term is going to be something, what, greater than 0, right? It's going to be something greater than 0. So, yeah, does that make sense? Look, see, this whole thing, this is the number of columns times the n per cell, but this, the important stuff is right here in the alpha squared, the AJ. This is the grown-up AJ because it's a population effect. But here's what's going on, is that the expectation is this, when we take expectation, so this thing here under the null hypothesis will go to what? 0. That will be 0 under the null hypothesis because we have no treatment effects, leaving us with an expectation equal to error variance. Equal to error variance. So that's the logic for saying, you know what? Look at this term. What do you divide by? What's MS error equal to? MS error is equal to this thing. When we take the expectation of MS error, it's equal to just this. Just trust me on that. It's equal to just this. So in other words, if I want to isolate this, what's the correct denominator? Right, if I wanna isolate this to tell me if there's an effect, then the correct denominator for my F ratio has to be what? It has to be the error, right? It has to be the error. So under the null, the expectation is this. So that's why this F ratio is constructed this way by taking MSA over MS error. Because under that null hypothesis, this expectation is equal to the error term. If it's not equal to the error term, then this whole term gets to be what? Bigger, right? So you're gonna have error plus something, so therefore MS error becomes the correct error term. MS error becomes the correct error term to isolate what we're interested in the numerator. Okay. MS error becomes that correct error term because just by looking at the equation, we say, what's gonna isolate what we're interested in the numerator? And that's gonna be the effect for A. And that's gonna be for the effect for A. That makes some sense. Now that may take some time to kind of, we're not gonna test that very much on the final like that. That takes some time to sink in. And by the time, and we don't do very much of it, but when we look at random effects models in the spring a little bit, we have to know that becomes even more salient. So you're gonna see that concept again, and it's gonna kind of say, yeah, I get an idea for that. So the reason for why, the reason for why we're doing dividing by MS error, right? So I'll just ask the question again, is why are we taking MSA and dividing it by MS error? What's the answer we just need to know? If you have your foot in the door in it, then like, you know a lot, even if you haven't opened up the folder, but at least you know where to go to get the information. You know what's going on, right? Like we can show you 20 pages of math. If you know what it is, it's demystified. You go, well, that's just that. Even though it may be complicated, it's just this. So what's that reason why we're dividing by MS error?
It allows us to isolate what we're interested in the numerator.
Exactly. It allows us to isolate what we're interested in the numerator. And we say, well, how do we know that? That's a follow-up question. Your student who you're TAing says, how do we know that? Well, it's because it's based on the
Equation.
Yeah, but more. What's the equation? Based on the expected. Exactly. You're absolutely right. It's based on the expectations. It's based on the expected mean squares. And knowing that, and just appreciating that just a little bit, you've got your foot into understanding how theoretical statistics works. Even though you're never gonna compute the expectations, you go, wait a minute, well, the reason why we're dividing by certain error terms is because that's how the expectations work out. So in other words, what I like to say is that even when we don't go into theoretical details, there's a good reason why we're using MS error here, and MS error here, and MS error here. It's well-founded on theoretical statistical principles, that if those things aren't true, if those principles aren't true, well, then we're kind of in trouble. So they're intelligently derived, right? They're intelligently derived. Now, MS error ends up being the correct denominator for each one of these sources of variation. But in the springtime, right, well, in February, it's not always going to be the case. Because when we change the model a little bit, the correct error term may be something different than MS error. Okay? And that's just to prep us a little bit. So I'm going to say again that the correct error term might be something different than MS error. So what does that tell us? That tells us that MS error is not always equivalent to the error term. MS error is not always equivalent to what the error term is going to be. Because in the spring, when we analyze a random effects model, we're going to divide by a different denominator. And what's the reason why we're going to divide by a different denominator? We know it conceptually. What's going to be our reason for that?
Expectation.
The expectations, just that's how it works. And we could almost say that, I mean, if we were to put that into like an umbrella term, we say that's how the math works out. Right? The actual math works out that I told you not to say that though, but because I wanted to unpack what the math meant. But now you know what the math means, so it's like, well, no, the math works out that way. Yeah, the math works out that way, because that's how the expectations work out. When we take expected values of those mean squares, MS error ends up not being the correct denominator. Why? Well, because it doesn't isolate what we're interested in. So we're gonna actually have to look at those terms a little bit. We don't do it very much because it's not a theoretical class, and there's really no big mystery to it. We look, we say, what's a better error term here? And we're gonna find out it's a different term in the ANOVA. We're gonna actually, I'll spoil it a little bit, because I don't want to bug you over the holidays. You go, SSA, we might have to even divide that by MSA over MS interaction. MS interaction will actually become a viable error term. Yeah, a viable error term for our analysis. And you go, how the heck can that be? Well, we'll have to see. But the important thing is MS error is not always the error term. And, well, you can answer that, right? Why would that be the case? Why would that be the case? Why would MS interaction be useful as an error term in the spring? You already know. Yes, because that's how the expectations work out. Even though we haven't seen it, you already know the answer. Well, it's gotta be due, because when you take expected mean squares, something's going on there such that it isolates what's in A, and therefore the interaction term becomes the correct error term. Yep.
When you change the error term, does that change the statistic, or does it stay as an F statistic because of the methodology, or does it change the stack?
It's a really, really good question. What makes it an F, right? What makes it an F? Good question. So, is it an F statistic? So, does F exist because of the research we're doing, because it's an ANOVA, because of all that? Or does F exist because of how it's defined? So, if I do this, MSA, and I go, I'm gonna be a rebel, I'm gonna say MSA over MS total. I can actually get an MS total. Take SS total divided by N minus 1 gives me MS total. And I go, the heck with it. For this ANOVA, tired of MS error, I'm going MSA over MS total. Is that an F? Well, technically you could say, well, it's comparing one variance to another, but it may have very little meaning for what we're doing, right? Very little meaning for what we're doing, but because it's a ratio of variances, you could, in theory, call it an F statistic, but it may not apply to anything of meaning. Let me take a different example. What if I took MSA and I divided it by 5? I just took the number 5, MSA divided by 5. Is that an F statistic? But I tell you, I did analysis of variance, I did like random assignment to conditions, I did my ANOVA study, but I just decided I didn't like the way F was defined. So I went MSA divided by 5. Is that an F statistic? No. No, because you say, you know what, that F has no distribution. And same thing with that MSA over MS total. You don't want to do that because that's not the way to do the ANOVA, but that F statistic is defined very, very precisely so that it reflects quantities of interest. Yeah.
Just confirming, so you're saying you can have an MS over, or MSA over MS total, and it still gives you an F statistic, but you can't do an ANOVA.
Well, yeah, what's the MSA over MS total, technically you're comparing two variances there. Technically you're comparing two variances, so you could, if you wanted to, call it an F because the F is a comparison of two variances, but it certainly would not be telling you anything you want from the table, right? So the question is, could you, in theory, still call that an F? Well, sure. It's just that you'd have to figure out what the distribution is for that and how it's distributed. Because that F statistic would have to be distributed on what? J minus 1 and N minus 1 degrees of freedom. And that would actually probably be a pretty tricky distribution to go find and to get because you wouldn't have existing tables for that. But theoretically, you could still call that an F, it'd be just a poorly derived F. Yeah.
So just to further this discussion a little bit, when you see an F statistic reported,
Yeah.
is it assumed that, like, is it always MS error, or do you have to dig a little bit more to see exactly what they're?
Yeah, when you see the F statistic report in the research article, you can assume that it was computed most likely correctly, right? Same with the software. Same when you see it in the software, you can assume that based on the type of model you're selecting, that F was actually computed correctly. But the thing is you'll see, when you look at software, you'll see that, hey, it's actually using a different error term, but there's a reason why it's using the different error term. So when we look at things and, you look at the software and it says, hey, I'm computing MSA over MS interaction, you don't wanna look and say, oh my goodness, there must be a mistake, right? There must be a mistake because MS error is the error term. You don't wanna be doing that, because MS error is the error term under certain conditions like this. But in other conditions, in other theoretical models, like random effects models, it's not always the error term. The actual error term could be MS interaction. So when you see that in the research report, and researchers will tell you what their denominators are, often to help clarify what the ANOVA is doing, you're gonna say, there's a reason why they divided by MS interaction. There's a reason why they divided by MS interaction, and the reason is because of the model they're doing. You may even be able to, if they say, we ran a different type of model, you may actually be able to offer that as a critique and saying you used the wrong error term. And that does happen sometimes if they ran a different model, but they tested it as if it was a certain type of model. So oftentimes you won't have to be concerned with that, but you should recognize that the error term will change depending on the type of model. And again, that's getting into the random effects model, though I'm doing a little prep for the random effects model and the mixed model, which the error term is going to change. So there's our first glimpse at why that error term will change. So let's say, just to make sure this is clear, let's say you get a statistically significant, well, what do you get here? You get your F comes out to be 4 for the interaction. Let's interpret. So for your interaction, it comes out to be like 4, your F. What do you ask F?
Probability.
Yeah, what's the probability of U, right? What's the probability of U arising from where? Right? What's the probability of getting an F statistic like this under the F distribution? Therefore, when you look at that and that value is really, really low, right? That value is really, really low, and what the computer's doing is looking at it for the interaction and error degrees of freedom. So we're saying that F statistic under the null hypothesis arose from the F distribution, and let's see where it falls in that F distribution, and that's what it's telling you whether it's statistically significant. So let's say it does come out to be statistically significant. Let's say it comes out to be like 0.002, right? 0.002. So that's less than, say, 0.05. So P, and APA wants you to report the exact P values these days and not just go P is less than 0.05. They actually want you to report this, which is kind of nice because then you see the actual value. So let's say it comes out to be this. Let's interpret that for the interaction. We do an interpretation. Be the interpretation. So P comes out to be 0.002 for your F. And let's say whatever your F comes out to be, whatever it comes out to be, let's say F is equal to, say, 5, and there's your P value. So you want to try it? I don't like to eat in class, but I just need you for just a second. What would you say?
Reject the null.
Okay, what would be the, let's go through the long explanation, so I have time to eat. Really long explanation, with context and everything, start from the beginning.
The probability of the data under the null is so unlikely that we reject the null.
Good. The probability of the data, right? Probability of the data under the null hypothesis. What's the null hypothesis?
There's no interaction.
No interaction. No interaction where? In the? In the population. There's no interaction in the population, right? So in the population, we assume that those lines are parallel. So that's the probability of the data under the assumption that there is no interaction. Since the probability of the data is so low under this assumption, what do you choose to do?
Reject.
You reject, right? You say, could this data have arisen under this assumption? Could this data whatever the data, there it is, right? Could this data have arisen under that assumption? Yes, absolutely, right? Let's say your p-value was like that. Could that data have arisen under this assumption? Absolutely. But the probability that it did, what does this represent in terms of heads on the binomial? Like that's like, 5,000 heads in a row. Unlikely under this assumption, therefore you gamble, and you say, therefore, I think that in the population, there is an interaction effect. But remember, in your sample data, you're always going to see some non-parallelness just due to the data. What you're referring to is the population. Okay, so what we're referring to is the population. So there's your interpretation for the interaction effect, and the idea here we're talking about here is interpreting main effects in the presence of interactions. Well, we've talked about that. We were starting to introduce that idea. Let's just get to the take-home message, right? So if this comes out to be statistically significant too, A and B, can you interpret A and B even in the presence of the interaction? That's what we're talking about. That's a little bit of a deep issue. Let's look at it. What's the take-home message? If you have evidence for an interaction in your data, it is the interaction that should be interpreted first, at least, right? First. So whenever you do an ANOVA, you're actually not starting at the top of the ANOVA. You're starting over here, right? So you don't want to report to your reader, say, well, hey, there's an effect for A. Wow, there's an age difference. Oh, by the way, there's also an interaction. Why? Because the interaction tells more of the what? Tells more of the story. It tells more of the full story of what's happening in your data. So, difference in melatonin on sleep? Yes. But if there's an interaction with age, then you want to be able to tell the 70-year-old, don't take it, it's not going to work for you. It only works if you're less than 40. Yeah.
Is it theoretically possible to get an interaction but no main effects?
It is. It can happen with your data that the interaction could come out to be statistically significant, even though your main effects are a little bit stubbornly not quite so in some cases. Usually it doesn't happen that your main effects will come out and your interaction, but it is theoretically possible that that could happen. Yeah. Now the effect size measure here, well, what do we got? Well, we've got our eta squared. There's our eta squared. We recognize the eta squared from the one-way analysis of variance. What was the one-way analysis of variance? One what? One way? What does the one refer to? No, not one sample. All of it's based on the one sample we collected, but it's the one independent variable, right? One independent variable. This is what? Some of these I actually don't mention. X1 and X2. There's two independent variables, therefore it's a two-way. Yeah, two-way factorial analysis of variance. So we've got a main effect here, main effect here. So, and there's our interaction effect. There's our interaction effect. So our eta squared, we said for the one-way analysis of variance, well, we only had what? We only had one independent variable for the one-way analysis of variance. Therefore, we only had one eta squared to compute. There's only one eta squared. What was that? What is this ugly definition here for eta squared? Well, that's the sums of squares due to between over sums of squares due to, how do we define it? Total, yeah. So eta squared equals SS between over SS total. SS between over SS total. And that was for the one way. Well, you can see that it's going to become a little bit more complicated in the two-way, right? In the two-way, what are you also going to need? Well, you can take what? How can I get the effect for B? Go SSB over SS total. Yep. So how much variance is accounted for by A? How much variance is accounted for by B? And then I could also do the interaction. How much variance is accounted for by the interaction effect, right? And then we've got the leftover variance for error. Now, really important is that all of these partition, right? These partition into the total. Does that make sense? It was the same thing for the one-way analysis of variance, that the SS between plus the SS error goes into the SS total. Why does that make sense that that should be true? Remember, this is like the sandbox you're playing in. right? This tells you, that total variation tells you how much variation do you have to deal with. Now let's break it down into the different sources. But you need to know that denominator. You need to know what that amount is before it can be partitioned. Do you remember in the one-way analysis of variance, what did we say? We said, well, SSA over SS total, that cannot exceed what? It can't, exactly right. It can't exceed 1, right? So if ever you got an eta squared greater than 1, you say, how could that be? The denominator has to be SS total. It's the total variation possible, of which SSA is that special case, that subset of it. So theoretically, if you got the eta squared equal to 1, that means all the variation would be accounted for by the actual row effect, by the factor. So here we have eta squared for the different sources. So we can do eta squared for A, eta squared for B, and then what's the other one? Well, eta squared for SSA by B. So there's eta squared for SSA by B over the total. And that's perfectly okay statistic to compute. Let's say that my SSAB comes out to be 0.70. That's A by B. SSA by B is equal to 0.70 sorry, that's eta squared. It's not SSA by B. So eta squared for the interaction is 0.70. Let's draw a conclusion on that. Can we get one? There's our eta squared for the interaction. 0.70 interpretation.
Interaction accounts for 70% of the variance.
Right. Interaction accounts for 70% of the variance in our data. So you can kind of foresee a little bit how things get complicated. Things are not complicated when you're dealing with simple statistical designs. They get complicated when you're dealing with more complex, and when you get to multivariate, it gets infinitely complicated. So in factorial designs, we're only looking at 2 variables here. If we had a third variable, a fourth, and we're doing multiple regression, then a whole bunch of relations are possible. So let's look at this. We could compute something for effect called partial eta squared. Now, partial eta squared is going to be a little bit different than eta squared. So let's see how it's constructed. Well, eta squared is SSA over SS total. Let's compute the partial eta squared for A. Look at how that's computed. All right, just look at how that's computed for just a second, and let me know what you think. Observations of this. What's similar between this and this? So that's eta squared partial for factor A. The SS effect is equivalent to SSA. Makes sense, right? That's the effect for the given factor you're looking at. So SS effect in this case would be SSA. What about that denominator? What about that denominator? Well, look at the eta squared for A for SS total.
It's reduced.
It's reduced. Does everyone see it? What's missing from it? What's the deal, right? You have SS effect plus SS error, right? Plus SS error. But what's not there? Interaction plus what? And your other one. So what is this partial eta squared? I mean, if you think of the different statistics as salespeople, right? You think of like, what is that partial eta squared trying to sell you? They're going, you know what? Why don't you take your SS effect, start off the same exact way as you did for the eta squared, the same exact way. But look at that denominator. I mean, let's look at the denominator in eta squared. Up here, it's SS total. Can you give a marketing reason, like how the salesperson would sell it, for going, you know what, I can sell you partial, you're gonna like it. Why? Say, you do your scientific experiments like, oh, I'm only explaining 20% of the variance, what a bummer. How am I gonna build a career on this? No one's gonna accept this. And then partial eta squared comes around and says, I might be able to help you. What's partial eta squared doing?
You're gonna get a larger value.
Yeah, you get a larger value, I want to see it. Say, you know what? Take SS effect plus SS error, then you say, wait a minute, aren't I supposed to do it by SS total? Salesperson says, yeah, but SS total is what? Bigger or smaller than what this is gonna give you? It's gonna be bigger, right? SS total is gonna be bigger because it contains more. What does SS total contain? SS total contains SS effect plus SS error plus the effect of the other one, because there's two now, factorial, plus the interaction effect, right? Plus the interaction effect. So when you compute the effect for A in ordinary eta squared, you're going SSA over SS total. You're going SSA over SS total. What's partial doing here? Partial is doing what? Partial saying, you know what? Just take SSA plus SS error and get rid of this. Don't include B or A by B in the denominator. And what effect does that have? Well, we just said it. It's going to increase your eta squared statistic. Okay, it's going to increase your eta squared statistic. So, does that make sense? Now, I mean, it's, yeah, so what would you rather report? Partial eta squared or eta squared? Well, probably partial eta squared, because why is it called partial? The name of partial.
Because it's partial.
It's partial, right? Yeah, yeah, that's right, yeah. It's partialing out the other stuff, right? It's partialing out the effect for B and any effect associated with B, which is the interaction effect. So it's getting rid of that. It's getting rid of that effect, okay? Now, does that make sense? Partialing it out because it's not including it in here. Partialing out, not including it, this idea of partialing out, or like, let's just push this variance aside, is going to become a common theme when we look at regression and things like that, because we do that all the time. We partial out other variables. And that's what partial eta squared is trying to do. It's trying to do. So the question now, which one you're going to report? So now the question gets more complicated because someone says, what's your effect size? How much variance have you explained in your experiment? You did your study. How much variance did you explain? They're asking you this in the hallway. Well, now, what are the possibilities you're going to say? I mean, what's the first thing you need to say? Maybe you're presenting at the conference. How much variance explained? You say what? It's not going to be one answer. So you say, well, depending on the measure you look at, it could be this, it could be this, it could be this, because there's also omega squared. So there's going to be contingencies on what variance is explained dependent on what measure you use to report the variance explained. So what differentiates one variance explained measure from another? It's not just the variance explained anymore. So there isn't just the one effect size measure, which is the correct one. Right? What's the correct one? It's kind of like this, right? It's kind of like, we saw this with post hocs a little bit. Is there a difference? I don't know. Depends on what post hoc you use. There is if you use the Newman coils. There isn't if you use the Chaffee. Then you're on CNN and Anderson Cooper says, is there an effect of the drug? You go, I don't know. Depends if you look at this. And you say, are you familiar with post hoc tests? They all control type 1 error a little bit differently. It's not the same as just looking at the object and saying there's something there. So in this case, what's the issue? The issue is the variance explained depends on what term you use. So what differentiates how are you going to know more about the variance explained is by understanding what the formula does, not by listening to the words. So if someone says to you, the variance explained by factor A is equal to 50%, you have to ask the question or look in the article and say, how are they defining their effect size measure? Because without that, you have no idea what the actual thing they said actually means.
Why, in our previous discussion, you talked about how the interaction tells more of the story than just one effect or the other. So why is it justified to take out the interaction? Like, you would think that that's an integral role in.
It would seem like it's important, right? But what's the concept here? That's actually a good critique, right? We're getting that. It's kind of like, so which one do you report? Right? Which one do you report? I mean, let's look at it. What would be, in a very strong sense, the most honest one? I don't want to use the word honest, but kind of like the first one you should probably look at is the eta squared, right? Why? Because you ran the experiment with B, with AB, and the dump is error, right? So what's that justification for doing eta squared? Well, it's not because the interaction may be accounting for variance or not, because you can compute the eta squared for the interaction as well, right? You can compute the interaction eta squared too. So the eta squared, variance explained, is the most important one, but the rationale for removing it, right? For removing it, the B plus A by B from the error term, is simply which one do you prefer interpret, and do you want to put factors in there that are not directly related to the factor of interest. So when I take SSA and I remove B and A by B, I'm just trying to get rid of factor B because I don't want that variance I'm not gonna use the word polluting, but increasing that denominator into SS total. And there isn't necessarily one right way or wrong way of doing it, but you just need to know that the differences and be able to interpret them and be able to think about in terms of when someone says variance explained, you have a perfect right to look in the manuscript or ask the question, which measure are you using? Otherwise, what's the danger, right? What's the danger? What if I just say to you, my experiment explains 60% of the variance, 60% variance. What's your effect size? 60%. What's the danger? The danger is you don't know what statistic is being reported, so I could be reporting the partial eta squared, but maybe that doesn't give you the complete story because you might have other factors in there too. So the big point for now, and we'll talk about that more in the spring, but what it means to partial out and stuff like that. But the big thing now is that the word isn't enough. You have to know the statistic, you have to have an idea of what it's actually doing so you can actually make sense of what the actual statistical indicator is telling you. Make sense? That's really like the big thing here. See, we're walking into that area because we've already encountered it here. We've encountered it here with going, well, if there's an effect for the interaction, is there an effect for the main effect? What if you don't test the interaction effect? So we've got some kind of like, well, it depends on what you're actually testing that's going to produce the result. Now we have the variance explained, the eta squared. The value for eta squared is going to matter on how you're defining eta squared and whether you're partialing or whether you're not. So we got 3-way, 4-way, and higher order models. There's a few words there on that. What would be a 3-way and a 4-way and a higher model for ANOVA? Could we think of that? So what if I just, yeah, so instead of 2, I put a third term, right? I put a, third term here, and I go x3, okay, so I have x3, maybe I have like a couple levels there. Okay. Then what happens? Well, then I have what interaction terms? x1 by x2, x1 by x3, x2 by x3, so I have a whole bunch of 2-way interactions, and then what do I have? The 3-way interaction. Which one are you going to interpret first? The 3-way interaction. What does the 3-way interaction look like there conceptually? This. So let's say the 3-way comes out. Let's say that this is age. The next one is melatonin dose. And what's the third one?
Sex.
Okay. Right there. How do you interpret that? How do you interpret that one? I mean, what does it even look like, right? How do you even start thinking about it? So maybe there's an interaction of age and dose, but what?
Not an interaction between age and sex.
Okay, careful. If there's a three-way interaction between age and dose, but,
Also, like you said.
I agree with you, there is a three-way interaction, you're absolutely right. But how do you unpack it? So there's a interaction between age and dose. Now, how do you bring this in?
For each level of sex.
Yeah, unpack just a bit more, you're on the right track. Interaction between age and dose, but that interaction is not
The same.
the same, right? Make sense? That interaction between age and dose is not consistent across levels of the third variable, right? So the interaction plot changes depending on the level of the third variable. So if I were to try to, I mean, it's not hard to graph, but you can see how fast an ANOVA design can get complicated. There's one graph, there's two, like that, dun, dun, dun. There's an interaction. There's one interaction, there's another interaction, this is sex one, sex two. The interaction is not consistent across that third variable. Make sense? Okay, who wants to do four-way? Okay, there's a good reason why four-way ANOVAs are rarely done, and it's for the reason we're looking at now. How the heck you interpret it? Even the three-way is difficult. Mathematically, you can do a 20-way interaction if you want, but theoretically, it's like, this is actually gonna be hard enough, right? This is gonna be hard enough to kind of get a feel for what you're doing in your data and communicating the results. That, what's this gonna, we gotta just conceptualize it, right? So you got what is it? Age, by dose, by sex, by,
Time of day, I don't even know
how about state?
if that state.
Yeah, we sleep less than, say, people in Arizona, they sleep more, no, Californians, I don't know. Let's go state, and we'll go Montana versus Idaho. So, what does that look like in terms of a graphical representation? The interpretation of the interaction, go four-way now. So here it is, right? What does it look like? Can we do it? Start here.
So you're just gonna have two sets of two graphs?
Two sets of two graphs, right? So you're gonna say, so let's go back to what was this one? This was the interaction, right? The interaction was not consistent across sex, right? Well, the four-way would mean that this non-consistency of interactions across sex is not consistent across state. Say it again. Okay. The inconsistency of interactions across sex is not consistent across state. In other words, this has a different picture if we look at it for Montanans versus those in Idaho. Does that make sense? And plotting those graphs, I mean, never go higher than a four-way, never go higher than a three-way usually, even though, you know, that's one thing with Cisco now, say, well, it can allow it, and, you know, if you hear someone say, I'm doing a six-way ANOVA, you go, my goodness, you don't know much about ANOVA, don't do that, right? You gotta be careful, just because the software allows it, doesn't necessarily mean you should do it. But that's the idea of how that gets complicated. Yeah.
So the interaction, when you're talking 3 and 4, if those interactions were the same throughout, then there's not actually an interaction.
That's correct, right. If these differences were consistent across state, in other words, if this graph looks the same, right, this whole graph looks the same for Montana versus Idaho, then you don't have an interaction. But if those graphs, right, change depending on whether you're looking at Montana versus Idaho, so it's almost like you're profiling, right? You're saying, what do things look like for Montanans? What do things look like in Idaho? And if there's any differences happening there, then you've got that four-way interaction. But again, that becomes like really, really complicated, and it becomes really even harder to unpack statistically and try to figure out what is this actually telling about my data, right? Telling about my data. So definitely you're usually gonna stop at the three-way interaction. Now, this idea of simple main effects, we'll take a quick break. The idea of simple main effects, let's start with the two-way. So if we have a two-way interaction here, we have what? Age and dose right here. Well, what's a simple main effect? If we have an interaction between age and dose, and you find the interaction effect, what would you like to do next? Well, let's just graph it here again. So we have dose 1, 2, 3, there's dose. And then we have for the young, and then we have, let's say it does this for the old. Okay. Interaction, yeah, non-parallel lines. Well, what would be maybe the follow-up analysis here? So we've got age by dose, and then we consider the follow-up analysis. If you find the interaction effect, then what you're probably gonna wanna do is what? You're probably not just gonna say, well, there's an interaction effect. Okay, I'm gonna change this just a bit, okay? I'm gonna put this now here, put it here, like that. There, just to make it clear of why you wanna do this. What would you be curious in doing? Because that's an interaction effect. Suggest another analysis on this, a follow-up analysis. Can we think of one? Or I'm gonna make it even more so like that. Your data comes out to be like this. I say there's an interaction between age, old versus young, and dose, and I show this graph. Well, what's happening at dose 1?
There's no interaction.
Yeah, it doesn't look like anything's happening, right? At dose 1, is there a difference at dose 1? Well, maybe in the sample, but that's probably so small that it's probably not gonna exist in the population. Learning check, there's a difference in the sample. How am I supposed to know whether that holds in the population? How am I supposed to know whether this is statistically significant here, right? So, just as an aside for a learning check, I've got a small difference here and I go, well, that's probably not gonna make it. That's probably not gonna make it. What's gonna tell me whether this is gonna make it in the population? The what?
F statistic.
Your F statistic, right? The denominator. So watch. If I have this, see how it's slightly different over here? What's going to determine whether I have an interaction in the population? It's going to be my denominator. I mean, the numerator is going to be what it is, but if my denominator is not, well, what am I looking for in my F statistic? A big denominator or a small? Yeah, I want a small denominator, because then my p-value is going to come out. If my sample size is pretty small, I would expect that to become not statistically significant. As I increase sample size, then I'm gonna say, you know what? I do have a statistically significant difference because this is based on enough data, right? I have the power to detect that difference. Make sense? So if I do this, go back to what I was saying here, you know, when we look at this difference, we say, there's probably not something going on there. Well, we need an analysis now to examine whether something's going on there. Because when you plot it and you look at your means, you're gonna say, okay, I have an interaction, I've got an interaction, but what's a good follow-up analysis? You might wanna look at this, you might wanna look at this, and you might want to look at this, right? We need a name for those types of analyses. Oh, it's up here, okay, so it's simple main effects, right? So you're gonna say, well, let me do, what kind of analysis could you do here? You have two means. So at dose 1, what analysis can you do? Between the young and the old. You got what are these in here? These are cell means. What analysis would work there? T-test. Sure. You can do a t-test right there. You do a t-test at dose 1 to see if there's differences between those two groups. Or if you wanted to, you could still do an ANOVA there on 2 groups. There's nothing preventing us from doing an ANOVA there too. You can do the F test. You can do the F test. So you can do the ANOVA test. This analysis right here that you're selecting a value of one of the levels and doing the comparison at the other level, like this, that's called the simple main effect. It's a simple main effect. So let's do another simple main effect. We'll show after the break where they are in the data. It's another simple main effect here, right here at 2, right? Is there a difference? When dose is equal to 2, is there a difference? When dose is equal to 3, is there a difference? So what are those simple main effects actually doing? They are unpacking, in a sense, the interaction effect. They're saying you have an interaction effect, let's run some follow-up and almost like similar to post hoc, but not quite the same, and saying, let's run some follow-up analyses and let's see what's actually contributing to the interaction effect. Let's unpack that a little bit more after we take a break and have a sandwich.
Oh my goodness. Anybody else on what? Anybody else on the top is right here.
Yeah. I just did last 2 minutes.